All right, everyone. Hello and assalamu alaikum. Let's begin. So we were doing integration, and today is a very important session because we will learn how to integrate a number of different types of fractions today. All right. So we want to learn how to integrate a number of different types of fractions. So what have we done until now? What did we do in the last class? Uh, in fact, let me just give you a brief overview of what we've done since we started integration. We started with these basic functions that you can integrate directly: x power n, e power x, sine x, cos x, secant square, and then also secant x tan x, cosecant x cot x, cosecant square x. These are functions that you should be able to integrate directly. If x is replaced with ax plus b, we know that we would just have to divide by the derivative of that, which is a, and then this rule applies as it is. Then the first major rule that we did after that was this ln rule. So after understanding how to integrate some functions directly, these functions that are listed down here, these functions are the ones that need to be able to integrate directly. Then we started with integrating fractions. How can we integrate fractions? The first major rule for fractions is this ln rule, the log rule. How does that work? If we have a fraction in which numerator is the derivative of the denominator, the integral is ln of the denominator. All right, we looked at a number of examples of this, how we can somehow convert a fraction to that particular form by multiplying or dividing by a constant, and also how the integral of tan and cot is also done using this rule. Okay, tan and cot, both of these functions are also integrated using this ln rule. Then in the last class, we looked at this tan inverse rules. If a fraction cannot be integrated using the ln rule, this is another possible method that we have. If a fraction is of this form, such that in the numerator you have a constant and in the denominator you have two terms, in which one of them is x squared and the other is a constant, and there's a plus sign between them. So you have to have only two terms, one x squared term, one constant, and a plus sign between them. You can integrate fractions like these using the tan inverse rule. What does the tan inverse rule look like? 1 over x squared plus a squared. If you have a fraction of this form, you can write the integral like this. Now, in the numerator, if we have some other constant apart from 1, you could just write that constant outside and you would have 1 inside. In the denominator, this is something important. In order to use this rule, you need the coefficient of x squared to be 1. So if it's not already 1, you would need to make that 1. We looked at this, how we could do that by taking this number common outside as well. And then you write this constant in square form and then just apply that formula. If that constant is not a perfect square, for example, in this case, it was not a perfect square, we said we could write it as under root 3 over 2 and then do whole square of that, right? Under root 3 over 2 whole square, that's also going to be a square like that. This is how we used tan inverse rule. We looked at a number of different examples of this as well. So this is what we've done until now. How to integrate some functions directly, and then how to integrate fractions, in which we've done two rules until now. One was the ln rule and the other was the tan inverse rule. Okay, and now we need to start with the next rule that we have. So sometimes what happens is both of those rules do not work. So what if you had something like this, for instance? If you had to integrate 14 over x plus 2 and 2x plus 3. I gave you this example in the last session, 2x minus 3. How do we integrate a fraction like this? 14 over x plus 2 into 2x minus 3. Now, if you think about it, it does not follow any of those earlier forms. It's not any of those earlier forms. The derivative of the denominator cannot be there in the numerator. You can try simplifying this and try to understand what does that become. So this is 2x squared plus 4x minus 3x, which is plus x minus 6. So the denominator in simplified form is this. It's a quadratic expression, a derivative of a quadratic. The derivative of a quadratic expression is going to be linear. In this case, the derivative would be 4x plus 1. There's no way you can have 4x plus 1 in the numerator by multiplying or dividing by a constant. So you cannot do this using the ln rule. So what's the other possibility? Tan inverse rule. That's the other rule that you have done. That also cannot be used because in the denominator, we have 3 terms. Tan inverse rule requires that in the denominator, you should only have 2 terms, one x squared term, and there should be a plus sign between them, and then some constant. So it's not tan inverse form either. So what do we do with this fraction now? Now here comes another method for integrating fractions, and that is by using partial fractions. Let me write that down here. Integration using partial fractions. This is another possible method that you have. Now, what would you do? You would actually find the partial fractions of this fraction and break it down into 2 parts. Right? So what do you actually do in partial fractions? You break the denominator into parts. So in this case, you have 14 over x plus 2 and 2x minus 3. This is a proper fraction, right? It's a proper fraction. So what's the form that you're going to have for this? We have non-repeated linear factors in the denominator. So it becomes a over x plus 2 plus b over 2x minus 3. These are the partial fractions that you're going to have for this. Now you can find the partial fractions for this and then integrate those 2 fractions separately. Let's try this. Let's see what happens when we do this. Remember the partial fraction method, you would multiply this denominator on the other side and see what that gives you. So you have 14 identical to a into 2x minus 3 plus b into x plus 2. Okay. And now you can try inputting some values of x. How can you make this bracket 0, for instance? In order to make this bracket 0, you would have to input x equals -2. So we could start with that. We could say, let's input x equals -2 on both sides. When we do that, that gives us 14 equal to a into 2 into -2 minus 3 plus b into -2 plus 2. Now that's obvious. The second term is going to become 0. So we have 14 equals -7 times a, and the value of a turns out to be -2. So that's a. A is -2. Similarly, we could think of how we could make this bracket 0. 2x minus 3. How could this become 0? We could equate this to 0. That gives us x equal to 3 over 2. We put x equal to 3 over 2 now. Let's see what happens when we do that. 14 equals, now this bracket becomes 0, so the whole first term gets eliminated. And we have b into 3 over 2 plus 2. Okay, so that gives us 14 equals 7 over 2 times b, and b equals 4. We've got the values of a and b. That means the partial fractions for this fraction, what are they going to be? If we write them down, these are the partial fractions. The value of a is -2, and the value of b is 4. This is what we end up getting. -2 over x plus 2 plus 4 over 2x minus 3. These are the partial fractions that we get. Okay. And now, since we wanted to integrate this fraction, there's a plus sign between these 2 fractions. So we can just integrate them separately now. We can say integral of this fraction on the left side. That is the same thing as integral of -2 over x plus 2 with respect to x plus integral of 4 over 2x minus 3 with respect to x. And you could just integrate these 2 fractions separately one by one. Okay, that's what we can do here. Let's try this. Now, how do we integrate these two fractions? Now we think of the rules that we already know of, right? We have done the ln rule. Does that work here? What's the derivative of x plus 2? Derivative of the denominator. Derivative of x plus 2 is 1. If we have 1 in the numerator, we could use the ln rule, right? So how can we have 1 in the numerator? We can take minus 2 common and write that outside, and we're left with 1 over x plus 2 inside. And now this first fraction is going to integrate to minus 2 into ln of x plus 2. That's the integral of this first fraction. What about the other one? It's 4 over 2x minus 3. What's the derivative of the denominator? 2. So we want 2 in the numerator. Right now we've got 4. We can take 2 common outside. That leaves us with 2 over 2x minus 3 inside. So we have 2 into ln of 2x minus 3. And that is the integral that we were looking for. Okay. Now, there's one other thing that's important here. In integration and later on in differential equations, the next topic that we do, and in general, whenever you have a final result in terms of logs, in terms of ln, the examiner expects you to give that result as a single log term, as a single ln term. So right now we've got two different ln terms. We have minus 2 ln of x plus 2 plus 2 into ln of 2x minus 3. The examiner often has 1 mark for converting this final answer to a single ln term. Now, how would you do that? Could we use multiplication or division law of logarithms here? Well, the problem is we have these numbers outside. In this case, both of these numbers are the same, 2 and minus 2. As in the numerical value is the same, we can take one of them common. So if we take, for instance, minus 2 common outside, what does that leave us with? That leaves us with ln of x plus 2 minus ln of 2x minus 3. And now what we can do is we can use the division law of logarithms, right? Ln of something minus ln of another thing, this is subtraction outside log. It would become division inside log. So we could write it as minus 2 times ln of x plus 2 over 2x minus 3 plus c. That is your final result. So if the examiner does expect you to do this last step to convert these multiple ln terms to a single ln term. Okay, so you have to do this using the multiplication law, division law, power law of logarithms. And that's your final result. This is how you would integrate using partial fractions. So sometimes the ln rule does not work. The tan inverse rule does not work. What happens is in the denominator, you have factors like this. You can break those factors down by using partial fractions, and then integrate those partial fractions separately one by one. Okay, so that's another method for integration. Now, let me give you another example on this. Sometimes you could get something like this as well. So you could have, for instance, integral of 14 over, let's say you've got 2x, or let's make it 12 in case that will give us something in teacher. Yeah, so let's try this. 12 over x squared plus 7x plus 12. Let's say we have a fraction like this. 12 over x squared plus 7x plus 12. Now, how do you integrate this fraction? Remember the rules that we have? ln rule, tan inverse rule, partial fractions, until now, right? Does the ln rule work here? What's the derivative of the denominator? The derivative of the denominator is 2x plus 7. We can't have 2x plus 7 in the numerator anyway, all right? Okay, now what about tan inverse? It's not tan inverse form because the denominator has 3 terms. Tan inverse requires only 2 terms, 1x squared, 1 constant, No x power 1. We have x power 1 here. So tan inverse rule also doesn't work here. Partial fractions, but for partial fractions, we need factors in the denominator. We don't have that here. What do we do? Any idea?
We can make factors.
We can factorize the denominator. In this case, it's a quadratic expression, and it's an expression that we can factorize by breaking the middle term. Now, you won't have this hint in the question. You'll have to think of it yourself. Can you factorize the denominator? In this case, it turns out you can factorize it. So it becomes integral of 12 over x squared plus 4x plus 3x plus 12. Okay, so you break the middle term. And then this could be written as integral of 12 over, it will become x plus 4 and x plus 3. You get this factorized form. And now you find the partial fractions for this. 12 over x plus 4 into x plus 3. You say this is equal to a over x plus 4 plus b over x plus 3. You'll find these partial fractions and then integrated using the ln rule. Once you have found the partial fractions, each of these individual fractions is going to be of the ln form. You can integrate each of them separately like this. Okay, so this is also something that can happen, that the denominator would not already be factorized, but it will be something that you will be able to factorize using middle term breaking like this, for instance. Okay. Now, this is something that you can do after this. Let's look at another example now. So this is how integration using partial fractions works. Okay. Now let's look at another possibility. Let's try another integral. Let's say you have to integrate something like this. (3x minus 5 divided by x squared plus 9. We want to integrate this now. So we've done 3 different methods until now, remember? We've done ln rule for fractions in particular. We've done the ln rule, tan inverse rule, and partial fractions. Okay? These are the 3 rules that we've done. Now, what if you have something like this? Integral of 3x minus 5 divided by x squared plus 9. Again, it's a fraction. How do we think about this? We think of using the rules that we've done until now. ln rule. What's the derivative of the denominator? The derivative of the denominator is 2 times x. Can we have that in the numerator? Well, we can't, because we also have this constant. How we can't get rid of this constant, right? We also have minus 5 here. How do we get rid of that? We can't. So it can't be the ln form as it is right now. Yes, Abdullah?
Yes, sir. Can't we take minus 5 outside?
How can you take minus 5 outside? So I understand what you mean. If it was like this, 5 into 3x divided by x squared plus 9, if it was something like this, then you could write this 5 outside when it was multiplying. It's being subtracted here. We can't write this outside. How would you write it outside the integral? So if you have, for instance, x minus 5 with respect to x, if you were integrating this, the integral of this would be x squared over 2 minus 5 times x. 5 also has to be integrated. It's only when it's multiplying, it's only when a constant is multiplying with the whole thing that you can write it outside, because when a constant is multiplying, it does not change due to integration, it remains the same. That is why we can write it outside. If we had something like this, for instance, if we had 5x integral of that, we could write it as 5 into integral of x, but not when you have plus a constant or minus a constant. That cannot be written outside.
Okay, sir. Thank you.
Okay, so that will not work. So we can't write 5 outside. Okay, so the ln rule does not work. We already figured that out. Tan inverse, well, if you think about it, the denominator is of that form. So you have x square plus a square form in the denominator. Can we use the tan inverse rule? Will that work?
No, sir, because we need a constant in the numerator.
For tan inverse, we need the numerator to be a constant. That is not a constant here. So that also doesn't work. In the numerator, you have an x term as well. Tan inverse rule also does not work. Okay. Partial fractions. Can we do partial fractions here? We can't, because we don't have factors in the denominator, and we can't even factorize this, right? We can't factorize this. So how do we integrate this now? So all three of those methods that we have done until now for integrating fractions, they do not work in this particular case. Tan inverse doesn't work, ln doesn't work, partial fractions don't work. So what do we do then? There's a trick that we use here in problems like these. If it works, sometimes it works, sometimes it doesn't. In this case, what we can do is we can split the numerator. So remember that rule, if you have x plus y over 5, we can write it as x over 5 plus y over 5, right? So if we take LCM of x over 5 plus y over 5, what does that become? That becomes x plus y over 5. So we can do the other way around as well. We could write it as 3x over x squared plus 9 integral of that plus integral of minus 5, or you could write minus outside if you want, minus 5 over x squared plus 9 with respect to x. You could break it down into two parts like this. So what we're doing here is we're breaking the numerator. We're splitting the numerator into two parts. Okay? And now if you think about it, can we integrate each of these fractions separately? Is that possible?
Yes,
What do
sir.
you think? How do we integrate the first one?
The tan rule.
Tan rule? It's still not a constant in the first one, in the numerator.
ln would be used.
ln rule can be used in the first one. What's the derivative of the denominator? It's 2 times x, right? Derivative of the denominator is 2 times x. Can we have 2x in the numerator somehow? What we can do is, we can write 3 outside. And then inside we're left with x over x squared plus 9. This 3 is being multiplied, right? So constant multiplying, we could write that outside the integral. That works. Now inside we need 2x. So we can multiply by 2 inside to balance that, divide by 2 outside. And now we have the ln form here. This integrates to 3 over 2 into ln of x squared plus 9. This is the integral of the first fraction. Okay. Now, what about the second one? This is tan inverse form, because now we have a constant in the numerator and an x squared term plus a constant in the denominator. So this is tan inverse form. This is something that can be integrated using that tan inverse rule. What's that rule? Integral of 1 over x squared plus a squared. That is given by 1 over a into tan inverse of x over a. This is how this rule is given in the formula sheet. What we can do is we can write 5 outside if we want. And then inside, we would have 1 over x squared plus 3 squared. And now in place of a in that formula, in that rule, we've got 3. Just apply that rule now, minus 5 as it is, multiplied by 1 over a, that's 1 over 3, into tan inverse of x over a, that's x over 3, plus c, and that is your final integral. You could write it as 5 over 3, but that's it. That's as much simplification as you can do. That will be your final result. Is that okay?
Yes, sir.
So this is another thing, another idea, another trick that you can use sometimes. You can split the numerator. Now, it's not as such a separate rule as such. It's just a trick that you use sometimes to break the numerator like this. Okay. Let's take another example. Let's say you have something like this, integral of five y plus 2 divided by 2y. Let's say we had to integrate this. 5y plus 2 divided by 2y. We have to integrate this. I'm sorry. Let's use x here. 5x plus 2. We could use y as well, but then we would need dy here. Okay. So this is 5x plus 2 divided by 2x. We want to integrate it with respect to x. Now, what about this? How do we integrate this integral? Again, you can think of the rules that you have. What's the derivative of the denominator? 2. You can't have 2 in the numerator. ln rule does not work. It's not tan inverse form. You can't do partial fractions. But what you can do is you can break the numerator. You can break the numerator like this. You can write it as 5x over 2 separately. We have integral of 5x over 2x, sorry. 5x over 2x with respect to x plus 2 over 2x with respect to x. And now in the first fraction, x and x get cancelled, and you're just left with 5 over 2 with respect to x. In the second fraction, 2 gets cancelled, and we're left with 1 over x with respect to x. The first one integrates to 5 over 2 times x, right? 5 over 2 is a constant. How do you integrate 5 over 2? Just put x with that. Plus integral of 1 over x, that's ln x, plus c. That is how you would integrate this fraction. Okay, so this is how we can use this rule sometimes like this. Okay, now let's try a past paper question that uses some of these concepts. Now, so let's say you have something like this, 10x squared plus x plus 1 divided by 2x minus 3. So I'm taking this from a past paper question. You want to integrate this thing. Okay, so now let me know how we should start. How do we integrate this fraction? 10x squared plus x plus 1 divided by 2x minus 3 into x squared plus 4. We want to integrate this fraction.
Sir, we can factorize the numerator to see if there's any cancellation possible.
Okay, that could be one idea, but can we factorize the numerator? We can't.
So we could solve the denominator and see.
Okay, so simplify the denominator to see if it becomes the ln form, perhaps, in case it becomes that, right? Tan inverse form, it's not tan inverse form, that's clear, because we don't have a constant in the numerator. So the only thing you would want to simplify the denominator for would be to see if the ln form perhaps works, right? Let's try that. That will give you 2x cubed minus 3x squared plus 4 into 2x, that's 8x minus 12. So denominator simplifies to this. Now, what's the derivative of this? 6x squared minus 6x plus 8. Can you make it this somehow? By multiplying or dividing by a constant? You can't, right? Because here, the coefficient of x squared and x, they are different. And here, they are both the same in terms of magnitude. So there's no way we can multiply or divide by a constant to get that thing. All right, so the ln rule does not work. Tan inverse does not work. Generally, when the denominator is factorized like this, you have to use partial fractions. But still, you should check this quickly if the ln rule can work directly, because that will be very quick in that case. But if it doesn't, then what's the other option? Partial fractions. You have factors in the denominator. The denominator is factorized like this. When you have denominator factorized, you think of partial fractions. Now, you have to find partial fractions for this thing now. How do you do that? Nx squared plus x plus 1 divided by 2x minus 3 into x squared plus 4. Now, this is an actual exam question, okay? I think it was like 7-8 marks or something. So it's going to take some time because it requires you to do partial fractions as well. Now, let's find the partial fractions. What's this form? It's a proper fraction, first of all right? So we don't need to add another constant to that. The form is going to be a over 2x minus 3 plus, for the quadratic factor, we have bx plus c divided by x squared plus 4. These are the two fractions that we get. Now, let's find the values of a, b, and c. Multiply the denominator on the right side, on the left side, on the right side. Multiply that here. What are we left with? 10x squared plus x plus 1. That is identical to a into x squared plus 4 plus bx plus c whole multiplied by 2x minus 3. Okay, now we need to input some values of x to find a, b, and c. Let's see how we can make this bracket 0. Well, we can't. X squared plus 4 equal to 0. That does not give you any value of x. So what do we do instead? We could try something else. We could try perhaps making this bracket 0. How will that work? X equals 3 over 2, right? So you start with that. You start with x equals 3 over 2. What does that give you? X equals 3 over 2. Now on the left side, that gives me 10 into 3 over 2 whole squared plus 3 over 2 plus 1. On the right side, you have a into 3 over 2 whole squared plus 4. Now, this whole thing is going to become 0, right? When x equals 3 over 2, that whole term gets eliminated, and we can find the value of a from this. Okay, so that's giving me 10 into 9 divided by 4 plus 3 divided by 2 plus 1. On the left side, I'm getting 25. On the right side, we have 9 over 4 plus 4. That's 25 over 4. 25 over 4 times a, and then a equals 4. That's one constant that we were looking for. The value of a turns out to be 4. Okay. Now, what do we do at this point now? We need to find the values of b and c as well. We have run out of brackets. What else can we do? Now we can input x equal to 0, because when we input x equal to 0, b will get eliminated, right? Because b has x multiplying. Then we can find the value of c. Let's try that. We input x equal to 0. This is partial fraction. We've done this before. When we input x equal to 0, on the left side, we get 0 plus 0 plus 1. On the right side, we already know the value for a now. That's 4. So that's 4 into 0 squared plus 4 plus b into 0. That's 0 plus c into 0 minus 3. Let's simplify this. That gives us 4 into 4, that's 16, minus 3 times c. 3c equals 15. And the value of c turns out to be 5. That's the value of c that we were looking for. And now we need to find b as well. You can input another value of x. Try x equals 1, for instance. Use a small value that makes the calculations simpler. So I'm inputting x equal to 1 now. Let's see what that gives us. Let's input x equal to 1. When we input x equal to 1, that gives us 10 into 1 squared plus 1 plus 1. On the other side, we have a, which is 4, into 1 squared plus 4 plus b into 1 plus c, which is 5, multiplied by 2 into 1 minus 3. All right. Now, on the left side, we have 12. On the right side, that's 4 into 5, that's 20, plus b plus 5 into minus 1. And that's 12 equal to 20 minus b minus 5. And the value of b turns out to be 20 minus 5 minus 12, and that's going to be 3. B turns out to be 3. So we've got the values of a, B and C. That is what we were looking for. Okay. So now we've got the partial fractions. Now we have the partial fractions. Now let's see how we can integrate this fraction. Let's look at the integration part now. Okay. So we wanted to integrate this fraction. We have broken it down into two parts. The value of A is 4. So we have 4 over 2x minus 3. B is 3. So that's 3x. C is 5. 3x plus 5. We need to integrate each of these fractions separately now. Okay. How do we do this? What about the first fraction? 4 over 2x minus 3. How can we integrate this fraction? Anyone?
Allen rule.
Which two?
Allen rule.
Allen rule. We can take 2 common outside. That leaves us with 2 into 2x, 2 over 2x minus 3 inside. What's the integral of this? 2 into ln of 2x minus 3. What about the second fraction?
Sir, we can write it separately. 3x
We can
plus
write it
5 over.
separately. Allen rule does not work. Tan inverse doesn't work. Partial fractions we can't do because the denominator cannot be factorized. We can split the numerator. We can write it as 2 separate fractions. 3x over x squared plus 4. We could integrate this separately. And write this separately, 5 over x squared plus 4. Now, what about the first one? We can write 3 outside. Remember, in the numerator, we need 2 times x. Okay. So we can write 3 outside. You are left with x over x squared plus 4 inside. We can multiply by 2 inside, divide by 2 outside to balance that. Now this becomes the ln form. And you have 5 into 1 over x squared plus 2 squared. Okay. 2 into ln of 2x minus 3 plus 3 over 2. This is ln form. ln of x squared plus 4 plus 5. This is tan inverse form now. 5 into 1 over 2 into tan inverse of x over 2. And that's what your integral turns out to be. Okay. But now notice you've got multiple ln terms in your final result. You need to write that as a single ln term. Okay. This needs to be written as a single ln term. So how can we do that? This is 2 into ln of 2x minus 3, 3 over 2 into ln of x squared plus 4. How can we make it a single ln term? Any idea?
So the 2 and 3 over 2 can go to power.
They have to go to power, right? We can't use the multiplication law otherwise because we have different numbers outside. We can't use multiplication law in this form. We would first need to take these numbers to the powers. So we write it as ln of 2x minus 3 whole squared plus ln of x squared plus 4 whole raised to the power 3 over 2 plus 5 over 2 into tan inverse of x over 2 . And now we can use the multiplication law. Then we use the multiplication rule, right? This is addition outside log. Inside log, it becomes multiplication. Okay, so what do you get? This gives you 2x minus 3 whole squared into x squared plus 4 whole raised to the power 3 over 2. You have ln of this whole thing plus 5 over 2 into tan inverse of x over 2 plus c. All right. That is the result that we end up getting from this. Okay. This is what we get when we write it as a single element. Any problem with this?
Sir,
Yes.
sir, if we take 2 common from the equation above and we will be left with 1 over 2 ln, we can just underroot it. Can we underroot ln x square plus?
How can we do that? This is not an equation. Under root square, you can only do that if you have an equation. You can do that on both sides of the equation then, right? In this case, we have some expression. So let's say we have 5. You can't say that just take under root of 5 like this. These are two different expressions, right? 5 is different, under root 5 is different. If it was an equation on the other, right? If it was like this, x square equals 5, then you could take square root on both sides and you would say x equals plus minus under root 5. That would make sense. In equations, that makes sense, but you can't do that in an expression like this. Okay.
Okay, sir.
Okay. Any problem with this? Does this make sense to everyone? This whole process? Now we have 4 methods for integrating fractions. ln rule, tan inverse rule, partial fractions, and splitting the numerator like this sometimes. Okay. All right. Now let's look at another expression. Okay, now let's look at a couple of now. So we get partial fractions here. Okay, just give me a minute. Okay, I'll be back in a minute. Just give me a minute. Okay, so we're done with 4 rules by now. Integral of 5 over x squared minus 9. How would we do this? 5 over x squared minus 9, what's the integral of this expression? Again, let's think of all of those rules that we've done. ln rule doesn't work. Derivative of denominator is 2x. We can't have x in the numerator. Tan inverse rule, does that work?
Yes,
Is this
sir.
the tan inverse? Yes?
Yes, sir.
Sure?
Oh, sir, there is a negative in between.
There's a minus in the denominator. Remember the form 1 over x squared plus a squared. We need a plus sign here. We can't have a minus sign for the tan inverse form. This is a negative sign. So tan inverse does not work. Even if you think of taking negative common outside, it doesn't work, because if you were to take it common outside, inside you would still be left with 5 over 9 minus x squared, or you can say minus x squared plus 9. That's still not that form because now we have a negative sign with x squared. We can't have that. So it's not tan inverse form. Okay, what else? It's not a new form. You can use one of the rules that we've done already. How do we integrate this? 5 over x squared
Partial
minus
fraction.
partial fractions, but for partial fractions, we need some factors in the denominator.
Yes, sir, we can make factors.
We can make factors. We can write it as integral of 5 over x plus 3 into x minus 3. This is a squared minus b squared, which can be written as a plus b into a minus b. So we can break it down into two parts like this. Okay. And now we can find partial fractions of this fraction and then integrate it using partial fractions. Let's try that. So in this case, you would have 5 over x plus 3 plus, I'm sorry, what am I doing? You have 5 over x plus 3 into x minus 3. You find partial fractions for that, a over x plus 3 plus b over x minus 3. Okay, you'll find partial fractions and then integrate the two fractions separately. Okay, it'll take some time. You'll find the values of a and b and then integrate them separately. Does everyone get that?
Yes.
When you integrate them separately, you'll get an ln form, right? For the first one and for the second one. And then you can write those two separate terms together as a single fraction, as a single ln term. You can do that. Now, how many marks do you think this question would be? Any idea? This whole question?
5 marks.
5 marks. So some marks for partial fraction, maybe 3 marks for partial fraction, then 2 or 3 marks for integration. 5 or 6 marks, right? But if it comes in the exam now, it'll be 2 marks. Until a few years back, it'll be 5 or 6 marks, but now it's going to be 2 marks. The reason for that is, if you look at the formula sheet, they have given you 2 other forms. Remember, we have talked about tan inverse form. This is the tan inverse form, 1 over x squared plus a squared. Right below this form, they've given us 2 other forms as well. 1 over x squared minus a squared and 1 over a squared minus x squared. Now, these are 2 other forms in which in the denominator, we have 2 terms, x squared and a squared, but there's a negative sign between them. So the proper way of doing this would be partial fractions. However, if it comes in the exam now, since they have given the result in the formula sheet already, so they've already given you the final result from an integral like this in the formula sheet, it'll just be 2 marks because you can just look at the formula sheet, write down the integral directly. Now, let me explain what that means. This is 5 over x squared minus 9, right? Let me write that down here. So these are 3 different forms. They look similar. 1 over x squared plus a squared, 1 over x squared minus a squared, 1 over a squared minus a squared. We have done the first one already, the tan inverse form. But if we had 5 over x squared minus 9, like we had here. Now, the proper way, as I said, would be to find partial fractions, then integrate those 2 fractions separately. But in this case, since we're given this formula in the formula sheet already, x squared minus a squared in the denominator, we can actually write it like this. We could say it's 5 over x, 5 into 1 over x squared minus 3 squared. It's this form you can see. Constant in the numerator. X squared minus a squared in the denominator. In place of a, you've got 3. So without doing partial fractions, without showing that whole process of doing partial fractions, you could write down this result directly. You would say the integral of this is going to be 5 outside remains as it is, and then you have 1 over 2a. That means 1 over 2 times 3, because the value of a that you have in this form is 3 in this case. So that's 1 over 2 times 3 into ln of x minus 3 divided by x plus 3. And that's your final result. You would say this is 5 over 6 into ln of x minus 3 over x plus 3. That's exactly what you would have gotten by doing all of that process that we talked about above, by finding partial fractions, integrating those fractions separately. But now, since this rule is given in the formula sheet already, it would just be 2 marks in the exam, and you should be able to do it directly like this. Okay, so that's this form x square minus a square. Similarly, if it was slightly different from that, maybe let's say 18 over four minus x squared. If we had something like this, what about this? Now you have constant first and x square later. X square is the second term. You could write it like this: 18 into 1 over 4 minus x squared with respect to x. What does that become now? This is that form, the second form now. This one. Okay, so in the denominator, you can write 4 as 2 squared. So in that second form that we saw, in this particular form, in place of a, we have got 2 now. Okay, 1 over a square plus x square. We have 1 over 2 square plus x square. In place of a, we have 2. This is 2, where we had a. So what does this become then? 18 into 1 over 2 times a, 1 over 2 times 2, into ln of a plus x over a minus x. That means 2 plus x over 2 minus x. That is the integral that we get from this. 18 over 4 is 9 over 2. So that's 9 over 2 into ln of 2 plus x divided by 2 minus x plus c. And that's the integral that you get from this. Now, similar to tan inverse, the condition that you had for tan inverse, that in the numerator, you need to have a constant. You have the same condition here. In the denominator, you should have only 2 terms. One should be a constant and the other should be x squared, and they should be subtracted like this. And the coefficient of x squared, that has to be 1. If it's not 1, you would make it 1. So all those other things, the rules that we had for tan inverse, they still apply here. Instead of having a plus sign, we have a minus sign. If we have a minus sign, then we use this or this rule. Is that okay? Any questions, anyone?
Sir,
Yes.
sir, can we take a minus from denominator outside?
Yes, in this case, you could do that. If you take minus common here, what would that become? It will become 18 over x squared minus 4. And you have minus outside. All right. And then this becomes this form. You could use that now with a minus outside. And that's going to give you the same thing. So you'll end up with something like this, minus 9 over 2. If you were to use that earlier form, x minus a. So that will be x minus 2 over x plus 2 inside. And these two forms are equivalent. These two are the same. The reason for that is you have a minus sign outside, right? If you take this minus to the power here, I'm sorry, what is that? Yeah. If you take minus to the power here, it becomes power minus 1. That means you take reciprocal of this, so it becomes x plus 2 over x minus 2 modulus. And that's the same thing, 9 over 2 into ln of that. Now, You have x plus 2, you have x plus 2. In the denominator, you have x minus 2, they have 2 minus x, but it doesn't make any difference because there's a modulus. And modulus x minus 2 is the same thing as 2 minus x. Okay, because even if one of them is negative, the modulus makes it positive, right? So it's the same thing. So yes, you could do it like that as well by taking negative common outside, and that will also be acceptable. Make sense?
Okay, sir.
All right, so how many forms have we talked about now? 6 forms for fractions. ln form, numerator being the derivative of the denominator. Tan inverse form, constant over x squared plus a constant. Partial fractions, when the denominator has factors like this, you can break them down using partial fractions, integrate those fractions separately. Then there are 2 other forms of partial fractions, which we just talked about, which you can write directly from the formula sheet, okay? And then you have integration by splitting the numerator. Sometimes you have to do this. When none of those other rules work, sometimes what helps is breaking the numerator down into 2 parts like this, and then you can integrate those fractions separately. Now, let's look at the last method that we have for integrating fractions. And that is when you have improper fractions. Improper fractions. Let's see what we do with improper fractions. The last thing for today, integrating improper fractions. Now, let me take an example for this again from a paper. Okay, again, this is an example that carries something around somewhere around 7 to 8 marks. Okay, so it's a relatively lengthy process. So let's say you have a fraction like this. They want you to integrate 8x cubed plus 4x squared plus 2x plus 7 divided by 4x squared plus 1. We want to integrate this fraction. Okay, 8x cubed plus 4x squared plus 2x plus 7 divided by 4x squared plus 1. Now, think about this. None of those earlier rules work. ln rule does not work. Derivative of denominator is 8x. You can't have only 8x in the numerator. Tan inverse rule requires constant in the numerator. It's not that form. You can't use partial fractions. There are no factors in the denominator, right? So the other 2 forms of partial fractions, they also don't work. What about splitting the numerator? Do you think that would work? Splitting the numerator? Could that work? You could try, but the very first fraction, so some of the later fractions you could do, for example, 2x over 4x squared plus 1, you could do this using ln rule. 7 over 4x squared plus 1, you could do this using tan inverse. These 2 can be integrated, but what about 8x cubed over 4x squared plus 1? What about that? What about 4x squared over 4x squared plus 1? How do you integrate these 2? These 2 are going to cause problems, okay? So splitting the numerator is also not going to work. Now, what's special about this fraction is it's an improper fraction. Remember improper fractions from partial fractions? We talked about this. Degree of the numerator is greater than the degree of the denominator in this case. So whenever the degree of the numerator is either equal to or greater than the degree of the denominator, it's an improper fraction. In this case, the degree is greater. We talked about this in partial fractions. Let me just show that to you here. Improper fractions. Yeah, so this was what we did. When degree of numerator is greater than or equal to the degree of the denominator. In partial fractions, we only used to get this case when the 2 degrees were equal. But now in integration, the degree of the numerator could be greater than the degree of the denominator as well. In this case, you can see numerator is power 3, maximum power is 3 in the numerator. In the denominator, the maximum power is 2. So it's an improper fraction. Now for this, again, let me remind you of another topic that we did earlier, polynomials. In polynomials, we talked about this relationship between dividend, divisor, quotient, and remainder. And I told you this is going to come in handy later as well. Now, this is where we actually are going to use that. Dividend over divisor, that's quotient plus remainder over divisor. This is a rule that we did in polynomials. This is how we connect dividend, divisor, quotient, and remainder. If you have an improper fraction, what you can do is you can break it down into two parts like this, into quotient and remainder over divisor. So that's what we're going to do here. We would have to use long division here. We have to do long division here. Okay. Now, sometimes they kind of give you a hint about this in the question. As for example, they would ask you in the first part of the question to divide 8x cubed plus 4x squared plus 2x plus 7 by 4x squared plus 1. And then in the second part, they would ask you to integrate this fraction. But a lot of times, they would just ask you to integrate this directly without giving you any hint. So you should be able to figure this out. Whenever you have improper fractions, what you have to do is do long division, break it down into quotient plus remainder over divisor for integrating. So how do we start? We start by doing long divisions. 8x cubed plus 4x squared plus 2x plus 7. The divisor is not linear, so we can't use synthetic division. Those of you who remember that, we have to use long division. So it's supposed to be divided by 4x squared plus 1. X term is missing, so we can write it as 4x squared plus 0x plus 1. Now, what do we multiply 4x squared by to get 8x cubed? 2x. 2x into this whole thing, that gives us 8x cubed plus 0x squared plus 2x. Now you change the signs. This gets cancelled, and we have 4x squared. This also gets cancelled. 4x squared plus 0x plus 7. What do you multiply 4x squared by to get 4x squared? You multiply it by 1. So you have 1 into this whole thing, and that gives you 4x squared plus 0x plus 1, right? Now change the signs again. Minus, minus, minus. This gets cancelled. This also gets cancelled. 7 minus 1 is 6. This is the remainder. And right there on top, you've got the quotient. Now we know dividend over divisor, that's the same thing as quotient plus remainder over divisor. So now what we can do is we can break this fraction down into two parts. We can say this fraction could be written as, this fraction could be broken down into two parts like this. Quotient, which is 2x plus 1, plus remainder, which is 6, over divisor, which is 4x squared plus 1. So we've broken that fraction down into two parts like this. And now we integrate each of these parts separately. We could integrate 2x plus 1 separately, right? It's a simple integral. We could integrate this separately and integrate 6 over 4x squared plus 1 separately. Okay. So this is what we can do with improper fractions. It's dividend over divisor, that becomes quotient plus remainder over divisor. That is what we are doing here. And now we integrate each of these parts separately. What's the integral of 2x? 2x integrates to 2x squared divided by 2. What's the integral of 1? 1 integrates to x. Plus, what about the integral of this? We can write 6. So what form do we use? So let me ask you first. How do we integrate this?
tan form.
This is tan inverse form, right? We can write 6 outside, and from the denominator, write 4 outside, take 4 common outside. In the numerator, we're left with 1. In the denominator, when we take 4 common outside, what are we left with inside? X squared plus 1 over 4. Okay. And now we can write it in that tan inverse form. So let me actually first cancel this out. Outside, we are left with x squared plus x. 6 and 4 get canceled to give us 3 over 2. So we have 3 over 2 here. Now, this needs to be written in tan inverse form, right? What was the tan inverse form? 1 over x squared plus a squared. So we can write this in square form. We can say this is x squared plus 1 over 2 whole squared. 1 over 4 could be written as 1 over 2 whole squared. Now, let me write that rule on the side here. So you have that in front. This is what's given in the formula sheet. 1 over x squared plus a squared. That's 1 over a into tan inverse of x over a, remember? I'm just going to use that. In case of a, we've got 1 over 2. Let's apply that rule. X squared plus x plus 3 over 2 remains as it is into 1 over a. That means 1 over 1 over 2 into tan inverse of x over a. That means x over 1 over 2. Now this 2 and this 2 get cancelled, and we're left with x squared plus x plus 3 into tan inverse. This 2 goes to the numerator, and it becomes tan inverse of 2 times x plus c. That is the integral that we get for this. So how do we integrate improper fractions then? We break them down into 2 parts: quotient plus remainder over divisor. That's how this is integrated. This is another way to integrate fractions. Improper fractions, they're broken down like this. Now let me summarize all of what we have done until now. So we have learned how to integrate all of these functions, how to integrate these functions directly. And then we have learned how to integrate a number of different types of fractions. And these are all the different types that we have done. ln rule, the numerator is the derivative of the denominator, right? Tan inverse rule, when you have a form like this, constant over x squared plus a squared, right? We've talked about this. Partial fractions, when you have factors in the denominator, you can find partial fractions for that. And then once you have found partial fractions, the individual fractions that you get, they can either be integrated using ln or tan inverse form, one of those two forms generally. Then we have talked about those two other forms of partial fractions that are given in the formula sheet already. When you have x squared minus a squared or a squared minus x squared in the denominator, they can be integrated directly to these forms. And then you can break the numerator, you can split the numerator. Sometimes if you have something like this, for instance, x plus 1 over 2x squared. Now you can break the numerator into 2 parts. That gives you 2 separate fractions like this, and then integrate those 2 fractions separately. And then finally, we looked at how to integrate improper fractions. Improper fractions are when degree of numerator is greater than or equal to degree of denominator. You divide the fraction into 2 parts like this: quotient plus remainder over divisor. These are all the different methods that you have for integrating fractions. Okay. Now, if none of them work, the last resort that you would have would be to take the denominator to the numerator. So for instance, if we had something like this, 4 over 2x plus 1 whole raised to power 5. Now, this is actually something that you've done in paper 1 before. If you have 2x plus 1 over whole power 5 in the denominator, and you just have a constant in the numerator, you can just bring the denominator to the numerator. And this becomes a simple power rule like integration because the part inside is linear. You could use power rule here. Sometimes you have something more complicated, ln x over under root x, for example, if you had something like this. Now, none of those fraction rules are going to work here. You bring x to the numerator, and it becomes a product like this. And then you integrate it like you would integrate products. And that is something that we would actually be discussing in the next class, integrating products. That's called integration by parts. That's the product rule of integration. So if none of these rules work, we take the denominator to the numerator, treat it like a product, and integrate like you would integrate products. All right. So that's all that we've done until now. We will look at integration by parts tomorrow, inshallah. Now, just a reminder, I have past paper session starting from 13th of April as well. Those of you are interested, I have posted the link for that already. You can have a look at all the details there at in the registration form. The timings of the session, the cost of all of those different combinations that you can have. So it will be for paper 1, paper 3, M1, and S1. I don't teach S2 currently, for those who have been asking. It's just P1, M1, P3, and S1. Okay, you can find all the details in the link there. There's an early bird discount if you register by 5th of April. After that, it will be regular fee. The discount will no longer be there after that. So those of you who are on YouTube, you have the link in the chat box on the side. It's there in the description below as well. You can have a look at that. We will be doing a lot of past papers in those sessions, a number of past papers. So basically, there are going to be 3 different types of sessions we would have, as in the classes that we have. So for every component, we would have like 10 to 12 classes in total. For P3, it might be a bit more because we have more time until P3, and maybe for S1 as well. But it's going to be 3 different types of sessions. And one type of session we will be doing, so every week, in some sessions, we will be doing full-length papers. And in some sessions, we will be doing difficult questions from some of the the variants that we have not done in full. So for example, if we look at June 2023 papers, if we're talking about paper 3, it has 3 variants, right? Paper 3.1, 3.2, and 3.3. Now, what we would do would be, we would look at the thresholds for 3.1, 3.2, 3.3. Whichever paper has the lowest threshold, assuming that's going to be the most difficult of those 3, we would do that paper complete. And then for the other 2 variants in the next session, I would be asking the registrants which questions they found difficult from the other 2 papers. In the next session, we will just be doing the more difficult questions. Okay, not the whole paper, just the more difficult questions. Similarly, for November 2023, for instance, we would do 1 full paper for 1 variant. For the other 2 variants we'll be looking at, we'll be doing the more difficult questions that you guys asked me. All right. And then towards the end of the session, when we, for example, 1 or 2 days before paper 1, 1 or 2 days before paper 3 and M1 and S1, before every single paper, the day before that, and maybe the day 2 days before that, there will be sessions in which I'll be taking your individual questions as well as from any papers that we haven't done. So from any past papers, if you have any problems in those last 2 days just before the exam, for that component, we could discuss those questions in those classes as well, apart from the papers that we will be doing. Okay, so the session is going to continue until the exam day, until the day before the exam, of course, not the exam day. So for paper 1, for instance, it would continue until 1st of May. Your exam is, I think, on 2nd May. For M1 until 6th May. For S1 until 12th of May. For P3 until 14th of May. So the last couple of sessions for each component will be spent on solving any questions that you guys come up with, any last minute questions that you have before your exams. And then before that, every week, in some sessions, we will be doing full-length papers, and in other sessions, we will look at the difficult questions from the other variants that we haven't done, that you guys will be telling me that these questions are finding difficult, and we'll be focusing on those questions from the remaining papers. All right, so that's the plan. You can look at the other details in the registration form, and I'll see some of you there, inshallah. Now, So we're done with the part about integrating fractions in P3 integration. Now, tomorrow we will be doing integration by parts. All right. And then the day after tomorrow, in fact, tomorrow do we have an extra class tomorrow? No, we don't have an extra class tomorrow. Tomorrow we'll do integration by parts. And the day after tomorrow, we will do substitution. And on Wednesday, we have another class as well. So look at the schedule that I've shared with you on the WhatsApp group. We have an extra class at night on Wednesday as well. So on Wednesday, we should be done with the whole, with all the concepts of integration. And then on Thursday, you can bring any problems that you have from the worksheet apart from the ones that we've done in class. But we will pretty much cover every single type of integral that you could come across. So hopefully, by Thursday, there will be very few questions that you have from the worksheet, and most of them you would be able to attempt already. Okay, so make sure that you are practicing as well. That is extremely important. Otherwise, we'll start forgetting the stuff. All of these rules, they should be on your fingertips. So whenever you look at a fraction, you should quickly be able to think about all of these rules. That okay, ln rule could work, tan inverse rule. These are the conditions for tan inverse. You'll quickly see, okay, if this works or not. Partial fraction, we'll see whether this works or not, right? And then breaking the numerator, we'll see if that could help. Improper fraction. So you have to do a lot of practice of this and make sure that you remember all of these different methods that we have talked about. Okay. So revise this before the next class as well. In the next class, we will be doing integration by parts. I'll see you again tomorrow. If you have any quick questions, let me know. Otherwise, that is going to be it for today. Yes, Abdullah.
Sir, can you upload the worksheet?
Isn't the worksheet uploaded already? It's
No,
not?
sir.
Okay, I'm sorry about that. So I thought I uploaded it before, after the last session. I'll do it right now. Okay. So just so I don't forget later, I will upload it right now. Okay, so now you should be able to attempt, let me see how many rows of assigned questions. So you should start working on the worksheet now. You should now be able to do the first 3 rows of assigned questions, okay? And then after tomorrow, you should be able to do the 4th row as well. And then after Wednesday, you should be able to complete the whole worksheet. All right, so try that. It's uploaded now. You can start working on that. All right, I'll see you again tomorrow then. Allah Hafiz. Bye.
Allah Hafiz, sir.
Allah Hafiz.
Yeah, sir.
Allah Hafiz.